So yeah, I'm here to talk about Clojure. It's a little bit different from the other languages you've seen, so I'm going to try to show you a little bit more of it, but I don't have a lot of time, so I'm going to go very quickly. It's about 3 years old. It is a Lisp, but if you think you know Lisp or hate it or whatever, if you could just set any preconceived notions aside, I've made a lot of changes, enhancements, and structural differences with Lisps of the past. And in particular, Clojure is not a port of any existing Lisp or the standard Lisps. In particular, one key difference is that Clojure is functional, and we've heard the word talked about a lot, mostly in terms of higher order functions being, passed to functions and methods. But really, I think the core of functional programming is an emphasis on immutability and on referential transparency, on calling functions that are free of side effects. I wanted a functional language on the JVM for a couple of reasons. One, I'm a commercial software developer, and JVM and .NET are sort of the only two accepted platforms. But I wanted to program at a higher level. So Clojure is designed to support the kinds of programs that programmers write in Java. And my goal was to try to target the application space of Java. In particular, those commercial programs generally involve concurrency these days. So that's a prime objective of Clojure, is to support concurrency explicitly in the language. So you'll see the combination of the way it approaches immutability in its data structures with these built-in primitives for concurrency. It's sort of got a complete package for functional programming on the JVM. Clojure was also designed for the JVM. It's not a port of another language, and it was designed to be hosted, to interoperate with the host, to expose Java, embrace Java, call Java libraries. It shares with Java a type system, the calling conventions, and everything. It is a pretty much barrier-free interface to Java. So being a Lisp, it's dynamic, and of course now lots of languages are dynamic, and I've learned many things from Lisp. So it has the typical things. It's interactive. It has a REPL. It supports that kind of development. You can change programs while they run. In particular, it has that characteristic of Lisp that makes Lisps a Lisp, which is that code is data. You represent your code as data structures, and the compiler and evaluator evaluate data, not text. So it makes it possible to write programs that write programs, which is the key to macros and syntactic abstraction. Clojure has a very small core, half a dozen primitives plus some extra primitives for accessing Java, which means there's a good chance I could get that part right. In addition, it makes a major change to Lisp, I think, in lifting off of the data structure, which was the console that represented singly linked lists. It lifts that abstraction off of that data structure and allows the libraries to be built on top of an abstraction. And that's made the language much more powerful than Lisps have been in the past. And in particular, it also allows the power of Lisp to be extended to Java. In addition, Clojure is not object-oriented. I'll be happy to talk later more about that, but it's a feature of Clojure. Clojure has all the basic data types you would expect. In particular, it has good math that doesn't wrap. So arbitrary precision integers, doubles, big decimals, ratios, those are all represented by their Java capital letter types, except for ratios I had to add. It has strings, it has character literals, it has symbols and keywords, which are a little bit different. They're used for identifiers and for keys, but they're prime data types in Clojure. So you compose your programs out of these data types. There's Boolean literals. Nil unifies with Java null. They are the same thing, and they represent nothing in Clojure. In addition, it has regex literals. So these are the atomic data types. Then it has a set of data structure literals. Okay, so there's a way to write these data structures in your program, and they mean what they say here. Okay, a parenthesized set of things. They could be numbers, they could be anything, is a list. And lists are singly linked, and they grow at the front. Whenever I say grow, change, add, remove, there's quotes, because nothing actually changes. But they grow at the front. They have fast access time to the front, linear access time down the line. Clojure also pretty uniquely has immutable vectors, which are in square brackets. They support very fast indexed access. And in addition, they behave like array lists in that they grow at the end. in constant time. There are map literals. They're in curly braces. It's key value, key value, key value. Key could be anything. Value could be anything. All of the data types are values, so the key could be a vector if you want. Ditto the value. Commas are white space. Put them in if they make it more readable, but they're not mandatory. A set is in curly braces preceded by a hash, and that will be a unique set of things. Everything nests. That is the syntax for the language. There's nothing else. Those data structures are the code. There's a text representation, that's what I just showed you, and there's something called a reader, which can read that out of a file and turn it into the data structures. At that point, those data structures get handed to an evaluator, which compiles them immediately to Java bytecode where they're executed. That's if you ask for them to be evaluated. You can also use the reader to read data. It's a nice format. It's nicer than JSON or XML. But in particular, the syntax of the language is not really based around text. It's based around these data structures and how they're interpreted. And everything else is very simple. Everything that would have been an operator, a declaration, or anything else is a parenthesized list where the operator is the first thing. In addition, there are no statements. Everything is an expression. So it's a pretty simple language. This is a spell corrector written by Peter Norvig in Python. And I don't expect to be able to read this, although you might. It's not too bad. But I just wanted to give you an idea of the syntactic weight of Clojure. Python is an excellent target because I think it has one of the lowest syntactic weights of any language, given that it uses white space in the way it does. So the Clojure program is the same size. It's the same number of lines. And with the Python program, those are the two shortest versions submitted to Norvig. He had many people do them in many languages. These programs are roughly equivalent. So it's pretty, I'm not really going to have time to explain all this thing, but it has lots of cool features. List comprehensions, pervasive destructuring, all kinds of good stuff. Some syntax related to Java. You can access statics by namespace / the name. That'll work for methods or it'll work for data variables. There's a syntax with dots that allow you to get at members generically. A member could be a member of a static thing or a member of an instance. And, of course, Clojure has macros, and what you're seeing here already is a macro. ... will take an arbitrary number of things, and it'll put dots in between them as if you wrote that Java. So that's system.getProperties.getJava version. We can call new. We can also call new like this. Again, though, we have macros, so instantly we can write code that's a lot shorter than Java. Java code that's a lot shorter than Java. Due to a new JFrame, add a new label with this name, pack it, and show it. You know the Java that is that, which involves a lot of this dot the thing, that dot the thing, that dot the thing. And in fact, this is the expansion. So like most Lisps, there's a really tiny core, and the rest of the language is written in the language in terms of macros and functions. The Java interop is complete and good and wrapper-free. Okay, you say import this thing. You're using Java. There's no wrapper classes, nothing in between you and these calls. I'll explain that a little bit more a little later. Okay, this is sort of Clojure's reason for being. The idea here is to allow people to do functional programming in a way that's roughly as easy as programming in Python or Ruby. And it starts by making all of those data structures that you saw immutable. So you write these literals and you program with these objects, but they cannot change. Like really, really can't change in the all their members are final kind of way. You couple that with a set of library functions, a huge set, that manipulate these data structures that have no side effects. So these functions take arguments, they produce new values, they don't change things. And this really makes for better programs. Your programs are easier to understand, easier to test. Mock object is kind of a joke. That object is mocking you for needing it. But I think that even if you set concurrency aside, functional programming yields better software. But when you put concurrency into the mix, I think functional programming is a huge, huge win for many reasons. And of course, you read Brian's excellent book, and how many times does it say immutable? Many, many times. But it's hard. Clojure makes that easy because it's the default. It's really functional, like let-bound locals are immutable. I didn't even call them variables because it would just be too disappointing. There's a functional looping construct which sort of works around the fact that there's no tail calls. And of course, it does also have higher order functions and that kind of thing. The library, this is just a small taste of it, for sequences is extremely powerful, and it allows you to write programs that when you read them, they explain what they're doing, as opposed to, imagine the equivalent loop you would have to write in Java, and imagine reading that loop to try to determine, oh, he's splitting this up into pieces. Oh, he's putting these in between those. These functions tell you what they do. But there's a couple of things that are interesting about sequences. Like I said, it's an abstraction on the list concept of Lisp. But because it's based around an interface in Java, it means that it can be implemented on many data structures, not just lists. And in fact, all of these functions and all of the sequence functions in the library are supported on all of the data structures of Clojure, on Java strings, Java arrays, everything Java iterable, all Java's collections. All of this stuff works on all of that. So it's very nice. Another aspect of raising that abstraction off of a concrete data structure means that we can implement sequences lazily. That cycle function returns an infinite sequence of numbers. Okay, take only uses the first 9, but it returns an indefinite amount. All of these functions and the vast majority of Clojure's sequence functions are lazy. That is to say, they do not produce a complete result. It's another advantage of not working on a concrete data structure, is that your intermediate computations do not need to return a complete intermediate data value. You can concatenate a bunch of operations and walk through it, and it's effectively like pulling on a pipeline. You're getting one thing at a time. You're trading off some ephemeral garbage for never needing to have a giant data structure or a set of giant data structures in your program. So it's all very pretty. Oops. In addition, there's equivalent set of functionality for maps and sets. You define, well, def just makes a top-level variable, right? We have a little literal map. Maps are functions of their keys. Sets are functions of their keys. Arrays are functions of their indexes because, well, they really are. And so Clojure lets them be that. So you can call a map, passing it a key, and get the value at that position. In addition, there's a little extra sugar. Keywords themselves are functions of associative things. So we can look up something in a map by just doing that or that. We can access the keys of a map, the values of a map. There's all kinds of functionality associated with maps. Associate or assoc is the way you would associate new keys and value pairs with an existing map, and you get a new map. M is not changed by that. And there's some really nice functions, right? You need to walk through a bunch of maps and increment counters per key. That's it. Merge with plus. A map and a set of other maps. Happens automatically. You want to build list, you merge with conj. Move up a level, working with sets as a set of set logic, union, intersection. Move up one more level. Sets of maps are relations. And there's a relational algebra for that. It's a neat one because it doesn't require rectangles. So I said everything's immutable, which should be scary, because immediately people say, oh my God, the amount of copying must be incredible. And it's not viable to do full copying. So there's this notion of persistent data structures. It's an overloaded word, like all the overloaded words we have. In this case, we mean, of course, persistent data structures are data structures that are immutable. We're making a new version. It's cheap, and both the new and the old version are available after the operation. And both the new and the old version support all the operations of the data structure with the same time characteristics as are promised by the data structure. So you can modify an element of a vector in constant time. And both the new and the old version have access to the elements in constant time. So they can't be full copies. Making that copy can't take a linear amount of time, or that wouldn't match the performance guarantees. So, of course, the trick is to use structural sharing. But it ends up that vectors and maps are hard. Persistent data structures, lists you see all the time, binary trees, red-black trees, easy. But log n is usually the best you can do. Clojure's persistent data structures are particularly neat. They're sort of the secret sauce of Clojure. I based them around Bagwell's bitmap hash trees, but I made them persistent. His design was not persistent. They're much faster than big O log n. They're actually big O log 32n, which is a great example of the difference between two things having the same shape and one being practical and the other not. The constant factors matter. And this is a little bit of how the representation looks. A bitmap hash tree divides the hash into 5-bit vectors, which are used for 32-way branching. Yeah?
Excuse me. Your basic state structures, are they implemented in Clojure or in Java?
Java. There are interfaces. There are Java interfaces for absolutely everything I'm showing you. This library is completely factored into a set of abstractions. There's abstractions for sequences, lists, maps, vectors, associative, reversible. It's a nice set of abstractions, and you can use it from Java. OK, we're doing fairly good. So that's how it works. So it's efficient to use these persistent data structures, which makes it practical. And that was the key problem I had to solve for Clojure, because I couldn't convince professional developers to use this if I didn't have hash tables, really. Everybody needs them. So now I'll talk a little bit about concurrency. I'm not really talking about data parallelism, like the kind of stuff they were talking about in the Fortress talk. I have some support for that. I have a wrapper around fork join and do some of that stuff. But here I'm really talking about task-level parallelism, the coarse-grained parallelism most applications do when they set some threads off to listen to a socket and a couple more to talk to the database and a couple more to deal with the web. And this is a big part of the architecture of Clojure. So what do we do now? Right? We have direct references to mutable objects. This is a Java program and really any object-oriented language that isn't sort of special. Right? So we're talking Java, Python, Ruby. They're all the same in this way, in that they unify identity and value. So we have direct references to mutable things, which means if we're going to have concurrent operations that might change them, we have to use locking. In Clojure, we're going to add back those method handles, right, or those object handles, in order to get an indirection between a mutable reference and an immutable object. It's inspired by SML's ref. And then Clojure adds concurrency semantics for the references. There's 3 different reference types, which now means that the language can help. It can enforce these concurrency semantics. And you end up with no locks on the user side. So this is what happens now. There's going to be many points in your program. They're pointing to a chunk O memory. Okay? And that chunk of memory is the identity of the thing. So once that's the case, they have to take care of all this stuff by themselves. Right? Any kind of consistency for that chunk of memory, they have to arbitrate, and there's no language level support for that. So in Clojure, what we do is we have an indirection. They're going to point to this box. That's their identity. That box, in turn, points to an immutable data structure. Any of the things I showed you. It could be a vector, it could be a map. It's often a map. People will, in Clojure, use those maps instead of where you would use objects. So we separate identity and value. To obtain the value, you have to dereference. The values can never change. So you can never get an inconsistent value. If you've got the value, you're safe. And you can share it easily between threads.
Are you not allowed to nest references inside of other things then?
Sure you can. This is the real, if you ever read Henry Baker's paper on equality, Clojure implements egal, he called it, where equality flows through until it hits a modifiable thing, right? And then 2 modifiable things are only equal if they are the same modifiable thing. So you could have a member of a structure that was a reference. But I don't recommend it. the one time you would do that if you want to try to sort of control your concurrency, maybe lighten up your contention by having more references.
Rich,
Yes?
when you showed us the syntax, I don't remember where the mutable cells came in. You said
This is still an abstract description. I'm going to show you the 3 variants of these cells.
okay.
So we haven't seen how to use this yet. This is the concept. So the concept is we have a reference to a thing. What does it mean to edit something then? Okay, well, we're going to have this immutable thing. We just saw a bunch of cool functions that can take one immutable thing and make a new one with some changed value. So that's what's going to happen. A new value is a function of the old value. They may share some structure. It's all immutable. It's all fine. It's all thread safe. No problem. Never impedes the readers. If you're reading this while somebody's creating that, again, no problem. And then we edit. Okay? The trick is this swap, to say this now points to that, that's under the system control. There are semantics for that in all cases. No munging about with no control. So it's always coordinated. There's 3 semantics. I may get to show you 2. The next dereference will see the new value. Any consumer of either value is unaffected by this edit. So I've been talking about references generically, that box. There are 3 kinds. They're called refs, agents, and vars. Refs allow coordinated change, and it's a transactional system. Agents are asynchronous, autonomous change. You can think a little bit about actor models, but the difference between Clojure's agents and actors is you do not require message passing to read values from agents. Vars are thread local. So in all cases, you have a safe way to change things. Whew. All right. Refs and transactions. Clojure has an STM. It's my own homemade STM. I have big differences with the design of a lot of STMs because I think they're designed to allow you to keep doing what you've always done, which is work with mutable objects, and they're just going to turn every mutable field into a tref or whatever. I don't actually believe that's going to work, but good luck. So it's an STM. It has what your usual expectations of transactions. In fact, it very much maps to what you think of when you think about a database transaction. I have an atomicity, isolation. I also have consistency. You can hook up a consistency function to any of these refs, and it will be run before the state will change. You don't pass, doesn't change. I don't have durability because this is an in-memory system. Right? And then it's basically everything happens or nothing does. Right? Your usual expectations. The big difference with an STM is that transactions are speculative. They may get run more than once. Okay? They're going to happen. They may get to a point. They may see somebody else won. They'll try again. So you have to avoid side effects. I actually can't help you with that because you can call Java, and I can't tell if that's going to be okay or not. Very easy to use. All you do is you surround your code with dosync. Any number of changes to references, either directly in that body or in any function that calls, will participate in the same transaction. If those are in turn in their own transactions, they join the outer transaction. I use multi-version concurrency control, which is also a unique part of Clojure's STM. It means that readers see a consistent snapshot view of the world. Readers don't have to get restarted to the writers ever. And there's no read tracking. So this is what it looks like to use it. We'll define foo to be now a reference to this map. Okay? We can dereference foo. We see what's in there. We can grab the value of foo and make a new value. We haven't really changed foo. We're just playing with its value. Foo is unchanged. This function is one of the transactional functions. There's alter, commute, and set. Commute takes a function, takes a reference, a function, and any arguments. And we'll run that inside the transaction, except I didn't start a transaction. So, not okay. Again, the system is helping. You tried to change something outside of a transaction, that's not going to happen. Wrap that same thing in a dosync, and it works. I only have 5 minutes left, so I'm not going to have too much time to talk about this. Agents do independent state. It's sort of a message system where you say send. The things you're going to send are going to be functions. They'll make the change in a thread pool at some point in the future. There's no way to coordinate more than one of these changes at the same time. They're not the same as actors. What's cool about it is it looks very similar. Foo is an agent with that value, we can dereference it the same way. We can send foo, a function, with arguments. It will change at some point in the future. If we immediately went to read it, maybe we wouldn't see that change. If we wait, this basically puts a message in its queue and waits for it to be consumed. Now we know this will have happened. We'll see that if nobody else is also talking to foo. The Java integration in Clojure is very good. There's a lot of unification. Clojure strings are Java strings. The numbers are the numbers. The collections all implement collection. My functions and closures are runnable and callable. Pass them to executors. It all works perfectly well. Everything I've shown you, all the core abstractions have interfaces. So they're very easy to consume from Java. It's also easy to extend Clojure from Java or Clojure. As I said before, the sequence library works on everything. You can implement and extend Java interfaces and classes in Clojure. And I have primitives support, which I'll show you in a second. From an implementation standpoint, I compile dynamically to bytecode in memory. I use ASM. It's great. I don't do any ahead-of-time compilation right now. Every function turns into a class. One interesting thing I think about Clojure is that those function objects actually have an overloaded arity. So you can pass a function object that has multiple methods with different arities. So it doesn't do any arity munging together. And it can be very fast. You can pass a function that might be called with 2 arguments or 3, and they'll both be as fast as possible. All my signatures take and return objects. What's cool is my variadics are built on those sequences. So you can write a function and pass it an infinite set of things, and as long as it doesn't try to use them all, it will work. Calls, all the function calls are straightforward method calls. 60 seconds. So there's no type system. I don't have any thunks. I don't put any extra arguments in. It's very easy to call from Java. You can call Java. There's only 2 things that are going to happen. It'll either be a reflective call or it'll be a direct call, right? There's no wrappers, caches, thunks, none of that stuff. I support type hints. With the very slightest bit of type hints and inference, I can make all of your Java calls direct calls. So there's no need for reflection, and I personally don't need invoke dynamic because of this. It's amazing how few hints you need. I do support locals that are primitives. So I make them into primitives. Then I inline the math calls to static methods. As James said before, that's as far as you need to go. I make a static method call, hotspot, turns it into primitive math. This is the code in Clojure. This is the speed. It's actually really pretty good. But you say int, and boom. That's exactly the same amount of time it takes Java. It's exactly the same bytecode after hotspot's finished. So in your inner loops, if you need to do fast math, I support primitives and arrays of primitives. It's exactly the same speed as Java. My STM implementation is very interesting. I'd be happy to talk to anybody about it who's interested in STM. The 2 things I would ask for, if we're asking for things, I'd really love tail call optimizations. It's a big deal. It's a big criticism of Clojure, being on the JVM. Ew, JVM has no tail calls. I've worked around it considerably. I think between loop recur and the lazy sequences, for people that bother to try Clojure, they find the pain of not having tail calls is not that great. I still want it. And as everyone has said so far, I would love tagged fixed nums or anything that makes working with box math fast, because I want to have people make those declarations. So to conclude, I've been very happy. I love the JVM. I think it's been a great platform. Because I directly targeted it and because I targeted 1.5, I'm not sitting needing anything. I work really well in 1.5. Clojure is really fast. There's 10 times as much to Clojure as I've shown you, but it does fill a nice niche. There is no dynamic functional language on the JVM. Now there is. It's Clojure. And I've only been out for a little bit less than a year, and uptake has been rapid, extremely rapid. So that's as fast as I can go.